Welcome all. In this session, the phasor representation of a sinusoidal waveform is discussed. The phasor representation is a very handy tool in circuit analysis involving sinusoidal signals. By representing a phasor diagram, we are representing a sinusoidal waveform with a phasor rotating in anti-clockwise direction with an angular velocity of omega t, which is equal to the angular velocity of the sinusoidal waveform. And the length of this phasor is, or length of this vector is proportionally maximum value of the sinusoidal waveform. In this figure, if you see here in this figure, we have plotted the variation of this waveform is equal to Em sin omega t plus phi, which is the most general representation of a sinusoidal voltage. Here Em is the maximum value which is taken to be 325 volt and omega is equal to, I have considered a 50 Hz supply. So omega will be equal to 2 pi into 50 and the initial phase of the waveform is 0. That means when omega t is equal to 0, E will be equal to 0. Initially, that is when omega t is equal to 0, the position of the vector is along the positive direction of x-axis, which is considered to be the reference direction. So at omega t is equal to 0, the vector is in this direction and the projection of this vector on the vertical direction is 0. That means the value corresponding to this point is this point, which is equal to 0. Now, if you imagine that this vector is rotating in the anti-clockwise direction, which is considered to be the positive direction with an angular velocity equal to omega, which corresponds to the omega or the angular velocity of this sinusoidal waveform. So when omega t is equal to say 30 degree, you can see that the vector or the phasor vector will be at this position, and you can see that the projection of this vector on the vertical axis will be equal to this quantity, which is equal to this quantity, and it corresponds to the value of the sinusoidal wave corresponding to omega t is equal to 30 degree. And now if you move this vector from this position to this position, that is omega t is equal to 60 degree, the corresponding projection of the vector on the vertical axis will be equal to this, from origin to this, that corresponds to the value of the sinusoidal waveform corresponding to omega t is equal to 60 degree. Now when the vector is at this position, you can see that when omega t, this position corresponds to omega t is equal to 90 degree, and the projection of this vector on the vertical axis is equal to the maximum value of the sinusoidal waveform. So the tip will be tracing the variation of this sinusoidal waveform, and when it is moved to 120 degree, 150, 180 degree, say when it has reached 180 degree, the position of the vector will be like this, and you can see that the projection of this on the vertical axis is equal to 0. That means corresponding to this point, you have this point on the sinusoidal waveform. And when omega t is equal to 270 degrees, you can see that this will be the position of the vector, and the projection of this on the vertical axis correspond to the negative maximum value of the sinusoidal waveform. And finally, when it has completed one complete revolution, or omega t is equal to 2 pi radians or 360 degrees, the vector will be at this position, and corresponding to this point, you get this. Now let us see an animation corresponding to this to make the picture clear. In this simulation, you can see that a sinusoidal voltage of maximum value 260 volt is considered. I have taken it randomly, and here on the x-axis, time in millisecond is plotted. So for a 50 Hz signal, you can see that corresponding to 10 milliseconds, the angle will be pi radians, and for 20 milliseconds, it will be 2 pi radians. Or vertical projection of this vector is equal to 0. Now if you move this vector in the anti-clockwise direction through say some 45 degrees, for example, it is here. Now it is approximately 45 degrees, and you can see that the projection of this vector on the vertical axis is this one, and that corresponding to the value of the sinusoid corresponding to this angle. Now if you further rotate by pi by 2 radians, the position of the vector will be like this. That means when the vector has rotated through pi by 2 radians, the position corresponds to the maximum value of the sinusoidal waveform, which corresponds to the value of omega t is equal to pi by 2 or 90 degrees. Now if you further rotate it by say pi by 2 radians in the same direction, in the anti-clockwise direction, the position of the vector will be this, and the corresponding position on the point on the sinusoidal waveform will be this. Now when it completes, or when the vector completes one complete revolution, you can see that the trace of the tip of this vector on the vertical axis, it has completed one complete cycle of radiation. That means we get a complete sinusoidal waveform. So if this vector is rotated with an angular velocity corresponding to the sinusoidal waveform, we get the trace of this sinusoidal waveform on the vertical axis. That means a continuously varying sinusoidal waveform, that means a sinusoid, can be represented as a vector rotating in anti-clockwise direction with the same angular velocity as that of the sinusoidal waveform, and the length of the vector is equal to the, or it corresponds to the maximum value of the sinusoidal waveform. Let us see the complete animation. Here you can see that the vector is rotating in the anti-clockwise direction, and when it completes one complete rotation, you get one complete cycle of the waveform. And here you can see that you have 2, 3, 4, 5 sinusoids are there. So when it has completed 5 revolutions, you get this. That is how we are representing a sinusoidal waveform as a vector. Now let us see how two sinusoidal waveforms with the same angular velocity but with a certain phase difference can be represented in the vector diagram. See, here two waveforms are plotted. One waveform, which is the blue trace with the expression Vt is equal to Vm sin omega t, which is considered as the reference waveform here, and the other one is which is expressed as It is equal to Im sin omega t minus phi. Here there is a phase difference between these two waveforms. That means this waveform is lagging with respect to this voltage waveform by an angle of 5 degrees. You can compare two waveforms, which is lagging with respect to the reference, or which is leading with respect to the reference. If you consider these two waveforms, here you can see that if you consider any similar points, for example, if you consider the maximum point on the two waveforms, here you can see that this is attaining its maximum value after this waveform has attained its maximum value. Here you can see that this waveform has attained maximum value at this position, but this waveform is attaining its maximum value after certain delay. That means this waveform is lagging with respect to this waveform by this much angle, which corresponds to phi is equal to 30 degree in this case. And here, or if you consider this as the reference waveform, you can see that the maximum value of this waveform is at this position, and you can see that this waveform has attained its maximum value before this attains its maximum value. That means this waveform is leading with respect to this by certain angle corresponding to phi is equal to 30 degree. And if it is expressed mathematically, it can be seen from here. Here you can see that this corresponds to the reference waveform, and there is a phase difference of 5 radians or corresponding degrees with respect to the reference here. That means here this waveform is lagging with respect to this by an angle 5 degrees. And here I have considered a voltage and current waveform. Now let us see how these two waveforms can be represented on a Phasor diagram. Here you can see that these are the two waveforms under consideration. Now if you take the voltage waveform or the voltage phasor corresponding to the voltage signal as a reference, that means Vm sin omega t, if you consider as the reference, the length of this reference phasor will be equal to the, or it will be proportional to the maximum value of the first or the reference waveform. That means the length of this vector will be proportional to the maximum value of this voltage signal. Now if you consider the phasor corresponding to this waveform, you can see that its length will be proportional to the maximum value of this sinusoidal waveform. And here it is not drawn to scale. But this phase difference, here you can see that the second waveform is lagging with respect to this waveform by an angle equal to 30 degrees. So it will be drawn like this. That means there is a phase difference of 30 degree between the reference phasor, and you can see that the positive direction is in the anti-clockwise direction. So if you have to mark a negative angle, you have to mark it in the clockwise direction. In the anti-clockwise direction it is positive, and in the clockwise direction it is negative. So if there is an angle of lag between two phasors, you have to measure it in the clockwise direction for lagging angle. Now if you consider if you rotate this in the positive direction, you can form an angle like this. Or if you consider the current vector as a reference, here you can see that this is the current vector, and this length corresponds to the maximum value of the current waveform, or this is proportional to the maximum value of the current signal. And here you can see that from this figure, this is leading with respect to the current waveform by certain angle. So it can be represented as phi is equal to 30 degree. So both conveys the same information, and both represent the sinusoidal waveforms in vector form. In this representation, we have taken the voltage waveform as reference, so it is drawn along the positive direction of the x-axis. And in this vector diagram, we have taken the current or the second waveform as reference, and the first one is leading with respect to the reference by an angle of 5 degrees. Now let us see the simulation showing these two waveforms. This vector corresponds to the voltage waveform, and this vector corresponds to the current waveform, and you can see that this current phasor is lagging by an angle equal to say 5 degrees. So always this phase difference will be maintained because the angular velocity of both the sinusoidal waveforms are same, and both the vectors are rotating in the anti-clockwise direction with the same speed. Now let us see how it rotates. See, always this phase difference is maintained, and the trace will be like this. It will be continuously varying, but this phase difference will be maintained always. Now let us see a leading case. Here we can see that this is the voltage waveform, and the current waveform is leading by an angle corresponding to say 30 degree or 5 degrees. Here also you can see that the phase difference of this phase difference will be maintained always while these two vectors are rotating in the anti-clockwise direction with the same speed. Now let us see the animation. Here you can see that both the vectors are rotating at the same speed, so this phase difference will be maintained always. So if you have these two sinusoidal waveforms, one is represented by say E is equal to Em sin omega t, another is represented by say I is equal to Im sin omega t plus phi, because in this case the current waveform is leading. In that case it can be, or the vector diagram can be drawn as, first the vector diagram or the phasor corresponding to the reference vector will be drawn along the positive direction of the x-axis, and the second one, if it is leading with respect to the reference phasor, it can be drawn with an angle of lead corresponding to the phase difference between these two sinusoidal waveforms. This is the leading case, and for the lagging case, the current will be drawn in the, or the angle of lag will be measured in the anti-clockwise direction, which is shown in this figure. In that case, you can see that this is the voltage waveform and this is the current waveform. And you can see that the current waveform is lagging with respect to the voltage waveform, because here you can see that this is the maximum point of the voltage waveform and this is the maximum point of the current waveform, and you can see that this is lagging, or this is attaining maximum value after a certain time delay after this has attained its maximum value. That means this is lagging with respect to this voltage waveform. So the main points to remember are, the phasor diagrams are drawn corresponding to time t is equal to 0 on the horizontal axis. The length of the phasors are proportional to the value of the voltage and the current, or the value of the different sinusoidal waveforms. And it should be the length should be proportional to the maximum value of the sinusoidal waveforms. And the phasors are assumed to rotate in an anti-clockwise direction, which is considered to be the positive direction. One phasor is designated as a reference phasor, and all other phasors will be either leading or lagging with respect to this reference. And generally, for the circuit analysis, the length of the phasors are taken corresponding to the RMS values. That means maximum value divided by root 2. Thank you for watching.